Hi everyone and welcome to this new video about AC steady-state analysis, and we continue with the maximum power transfer examples. This is our example number 3. In this example I would like to discuss a practical situation. We have an amplifier here which is connected to a speaker through a coupling capacitor such that we can block the DC signals, and the circuit diagram for this situation is also shown here. So the amplifier is modeled by a voltage source in series with the internal resistor RS, and the coupling capacitor is just one capacitor C, and the speaker is modeled by a series resistor and the inductor, so series RL circuit. So the amplifier is connected again through this through the coupling capacitor to the speaker, the amplifier, internal resistor, and the C will act in this example as the source, and the load will be the speaker, so that will be the series combination of the R and the L. Now the component values are also given here, and the source voltage is also given in the time domain. The question in this case is different, as you can see from the expression for the voltage source, the omega, which is most of the time given. It is not given in this case, so it is a general expression. So what is the question? Calculate the frequency for the maximum power transfer to the speaker. Now, let's look at the situation again and more carefully. What was the situation for maximum power transfer? The source impedance, Z of S, which we called it also in the previous examples, must be equal to the complex conjugate of the Z of L, so this complex conjugate of the load. But what the problem is the following. If I write down the expression for Zs and also write down the expression for Z of L, I will have the following problem. The real parts can never be equal to each other because these are all already given. So this 20 ohm for this and 6 ohm for this. So the real parts are 20 and 6. So that can never be equal to each other. I don't have any resistive components in the circuit, so it is impossible to make the maximum power transfer in this circuit using the maximum power transfer theorem. So what I can do at best is making the reactances of the capacitor and the inductor cancel each other. So the compensation of the reactive components will allow me to reach the maximum possible power delivered to the speaker. That's very important. So in this case, only in this situation, or in these kind of situations, so what you have is for this circuit, I can only say that the X of C, which is the reactance of the capacitor, coupling capacitor, must be equal to the inductor reactance, which is also, of course, in the speaker itself. So if I fulfill this condition and calculate the required frequency for this condition, then actually the complete the example is actually with this situation clear. So what we have is the following: 1 over omega times C, which is the expression for the X of C, is equal to omega times L. And if I rewrite this, I will get omega is equal to 1 over square root of L times C, which is a really familiar expression when you consider resonant circuits and RLC circuits. So what you get if you fill in the values which are given above, well, we get the following. L is 0.04, 40 millihenries, and the capacitor was 100 nanofarads, what will be 10 to the power minus 7. And if you do the math, you will get 15,811, so 15811 radians per second. Okay, if I want to convert this also to the frequency, so what I have is the following: omega divided by 2 pi, which is 15,811 divided by 2 pi, which will be close to 2,516 hertz. So if you operate your system at this frequency, you will have the maximum possible power transfer to the speaker. So if you, of course, move up with the frequency, so if you increase the frequency, so let's make it, for example, 1 gigahertz, very large, what will happen to the circuit? So this capacitor will behave as a short circuit because 1 over omega times C, so the omega is very large, so this is in practical situation very low, so let's assume it is 0, so this is actually a short circuit. This will be an open circuit, so actually there is no current flowing in this circuit anymore because of the very high frequencies. If you make it very low frequency, then this circuit will be open. So actually you will see two extremes. So if you make it very low and if you make it very high, you will get actually the situation of open circuit constantly because of the C, and other way around with the inductor L. And this frequency will allow you to have the maximum possible power transfer only in this circuit and not using the situation. So I will make it clear, don't use or cannot use, better you can say we cannot use the following: Z of C is equal to Z of ZL and the complex conjugate of that. We cannot use this. This is important. Why? Again, the RS is not equal to R, and I'm already, and this condition will fail for sure. Okay, this is example number 3. We will continue, of course, so keep in touch and have a nice day and good luck with the study.